Welcome, Mechanics of Materials students. This is our 5th lecture on beams, and in this lecture we're going to switch our focus from longitudinal stresses to kind of their effects. So if we have a flexural moment applied or some kind of loading that results in a moment, we'll get a longitudinal stress as a result of it, but we'll also get flexural deflection. And the easiest way to envision this is to imagine an originally straight beam here, showing in this figure. I'm outlining it in red. It's simply supported, which means it's supported by a roller at one point. This is for a 2D beam, simply supported, which can provide upward vertical force only, and then a pin over here, which can provide horizontal and vertical force, no moment. We're going to apply some concatenation of loads, distributed loads, point loads, whatever, that results in a net internal moment somewhere along the beam, which will in turn result in longitudinal stresses, but it'll also result in strains. So we'll end up getting flexural strains, which means strains in the y direction, or displacement in the y direction. We'll also get strains in the x direction, as we saw when we derived the flexure formula. So now we want to take a look at the actual displacement distance here, and this is little vx. This isn't big V, meaning shear force on the cut face of a beam, internal force. This is little v, meaning displacement or distance from the centroid of our original beam to its new position in the y direction as a result of the beam flexing. So you can imagine v changing as a function of x. It's fairly large and positive here. It's 0 as we go through this support, because it can't move up or down at the support. And then it starts to go negative, and it reaches our negative maximum somewhere around here. So this would be v negative value between this point, the original centroid, and the new centroid, and then back to 0 up here. So it's already looking ahead. Hint: we're defining a few boundary conditions that we'll make use of later to evaluate constants of integration. So along with our distance displacement, our flexural displacement little v, we can also define a theta angle, which is the tangent to the new curved beam shape at any point. So basically, if we draw a tangent anywhere to the edge of the flexed beam, and then we look at that angle versus our positive x-axis, we can define a theta at any point. Of course, it definitely changes with x. So using some geometry, we can relate theta to our displacement as a function of x, and we find that we can define the tangent of theta as our displacement vertically versus, so much distance over, basically rise over run. Definition of slope: tangent of theta is rise over run, which is v over x, and if we shrink the distance over which we're calculating that down to a single point, basically we're kind of thinking like definition of derivative. We can define that at a single point, tangent at that single point, as dv dx, or the change in vertical displacement due to flexure as a function of our position down the beam. For small thetas, we can make a small angle approximation and say that tan theta is approximately theta. So we can say that the first derivative of our height of displacement, so the beam, the new beam centroid position being above or below its original flat position, the first derivative of that displacement with position along the beam is going to be equal to the slope, or the angle, the theta angle that the beam is making as a result of flexion. So we can just define that simply by looking at the geometry of our flexed beam. And just as a note, this graphic with this exaggerated flexion, it is very exaggerated. in general, just to make this small angle approximation and to stay away from strains that would correspond to yield. They're not going to be anywhere close to that big. We're very, very small, and in fact would typically have to be measured with sensitive gauges. For a very, very long span, though, they could add up to quite a bit. And if we're looking at things like clearances or bearings, or maybe not having low points where water could accumulate, like on a roof or on a road deck surface, very small angles can still add up to very large consequences in terms of structural function. So, but generally speaking, we're talking about small thetas and fairly small but significant displacements, little v. Okay. So let's kind of start looking mathematically at theta, which changes with an x, and v, and see if we can't relate them mathematically to something that we can in turn relate to, I don't know, longitudinal stress, which we also already know how to relate to things like moment, internal moment at a given point along the beam, and all kinds of other stuff that we used when we derived the Flexure formula, because again, those are things that we can determine from simple statics or from elastic constants if we know the material. So the clincher here is to relate the angle theta to the curvature. So we're back to the shape that this beam makes as a result of flexure under applied loads. Okay, so if you recall from the derivation of the Flexure formula, when we were looking at a curved beam and all of the assumptions that went into being able to define the longitudinal strain, we came up with this relationship that longitudinal stress was related to the elastic modulus, the y distance above or below the neutral axis, which in the absence of stretching or compressing axial loads, forces, was the centroid. So how far above the centroid or below the centroid are you? That's this y. And then that was divided by the curvature at any point. And we went further and did some substitutions and actually got rid of that expression for curvature because it wasn't doing a lot of good when we were looking at ways to relate our longitudinal stress to other things that we could calculate easier. But we're going to kind of pull that back, and now we're going to revisit it because curvature is going to be the link between things that we can calculate easily and that strain, and the displacement. We already have longitudinal strain previously. The displacement, which is what we care about now. We want to know how much this beam sags or how much this angle changes, because we may be totally okay on our longitudinal stress in terms of having a great safety factor against yield and being well within our elastic limits, but it may just simply sag too much. We'll have a big puddle of water on a road deck, or our roof will sag too much, and then we'll accumulate water, which then might add some more stress. So we can have design criteria that is in terms of stress or in terms of deflection. So we're going to dance back and forth with expressions from our Flexure formula derivation, but we're going to be looking to get that little v deflection as a function of x everywhere in the beam, and look at under a different condition of loading and for a given shape of cross-section as contained in the moment of inertia IZZ material. Where's that a maximum? What is it? So with that segue, back we go to our derivation. So from our Flexure formula derivation, we've got this expression for longitudinal stress in the x, axial, longitudinal in the beam, and that is also equal to negative moment, internal moment at a given point x times that y distance from the centroid divided by the moment of inertia about the z-axis, which is sticking out from the centroid. So this time we're going to eliminate sigma xx because we want to look at displacement, we want to look at something more akin to strain. So we're just going to set these two equal, which means we're going to relate this to this, and we're going to solve for that radius of curvature, because that's what's going to relate to displacement. So we're going to basically isolate the beam geometry, the flexed geometry terms. So we set these equal, and we're going to leave this expression of 1 over the radius of curvature, because we can then describe that as the term small kappa. This is the Greek letter kappa, which is curvature, quote unquote, not, which is basically 1 over the radius of curvature. And this is an expression of how curvy our a line going through every point on the centroid of the cross section is. How curvy did we get? So basically kappa is big if the radius of curvature is small, so it's a tighter curve, it's curvier. Okay. Curvature, if you recall from maybe some dynamics, kinematics expressions, you might have used this definition. We can mathematically define how curvy a function is if we have a function defined on a continuous basis versus an independent variable, which in this case is going to be position along the beam, as the second derivative of that function with respect, in this case, to x, position along the beam, divided by 1 plus the first derivative of that function with respect to distance along the beam squared, the whole denominator of the fraction raised to the 3/2. Okay, so now we simplify this. We pull out our small angle formula again, our small angle approximation, because we got small thetas. So if we have a small theta, remember theta is tan theta is dv dx, so we're going to say for a small theta, theta is the same as dv dx, and if theta is small, then we can assume that dv dx, or the first derivative of our displacement function, our how much the beam has lifted up or sagged, is way less than 1. Small means less than 1, like close to 0. If this is way less than 1, then we can just kind of assume it's negligible. So the whole denominator becomes 1. So we can say that kappa, this curvature term, which in turn is equal to the internal moment at that point, divided by elastic modulus times the moment of inertia, the cross-section about its centroid in the z, again, shape dependent, all we need to know is the shape of the beam, is equal to the second derivative of that displacement as a function of x. That's what we wanted. We wanted displacement. So now we've got a function or a way to an expression, an equation for that displacement. It happens to be a differential equation, but this is no problem. As long as we have a continuous function for moment, and we know how modulus and the moment of inertia vary with respect to x, all we have to do is integrate twice. And we know what that displacement is, either going up or down, and we can identify the point at which it's a maximum, and then we can decide whether or not our beam is sagging too much. Okay, so we're 2 integrals away. So we'll just kind of step through those, and then we'll maybe take a step back and relate how this relates to integrating all the way back from a distributed load. Okay, so just to recall, our theta is equal to dv dx, and so our second derivative of displacement v with respect to x is like the first derivative of theta with respect to x. So we can integrate once, and we can get an expression for our angle, our slope of our beam, like a line drawn through the centroid of the beam, the slope of that line at any point. So here's our first integration pass. So we've integrated theta, we've integrated d theta from theta at some point x1 to theta at some point x, and also integrated the other side from x1 to x. Again, if we knew what the moment was, we would know how to integrate it. We could have an expression. In a lot of cases, for a beam that is a mill product, it'll have been extruded or rolled. It'll have exactly the same cross-section all the way along, and most of the time those same kind of manufacturing processes will give us very, very uniform properties, material properties. Modulus is very difficult to change even if we maybe had a little bit of difference in heat treatment or grain size or molecular weight or anything along that beam, chances are our E tensile modulus is going to be uniform. So we can take our EI, or our tensile modulus times the moment of inertia, out of the integral in those cases. So we can almost all the time assume it's constant. It may not be constant. If it's not, okay, all we need is how it varies with position. Maybe it varies piecewise. We could always incorporate that, but if we know it's constant, we just take it out. Then all we have to do is worry about how to integrate the moment as a function of x as we go along. Now remember, chances are, when you were solving your statics problem, looking at the point of maximum moment to get your longitudinal stress analysis done for your beam, you already integrated a couple of times to get a moment as a function of x expression, because you probably had a distributed load of some kind. Maybe it was constant, maybe it was, triangular type of expression, linear expression. You integrated once to get your shear force at any point along that beam, then you integrated again to get the internal moment at any point along the beam. You're just going to keep integrating with respect to x. So this is what you did here. So your angle, your deflection angle at any point along the beam, so the slope of the literal curve shape that beam is now making, is just going to be our integral of the moment expression divided by elastic modulus and moment of inertia, the cross section about the z centroid, plus whatever our angle was at the reference start of our integral. Which, by the way, given that theta is also dv dx, this should be an x, not a t, because I was thinking of kinematics there with all that curvature. So that reminds us that, if we want to get actual displacement, sagging, rising, basically think of a bent floorboard that you don't want to trip over. We integrate again. So all we have to do is take this entire expression, plop it into an integral, and we kind of cheated. We knew that we could integrate theta at a given point. This is now a constant once we've dropped in a given point, so we can integrate that again with respect to x and apply the upper and lower limits, and then we'll kick out another constant. And therein lies the challenge of this type of analysis. We now, if you noticed, we have one constant of integration. We had to know what the angle was somewhere, and we have to know what the actual displacement was somewhere. So that's the only trick to this analysis. If you do your statics problem and you have an x-dependent expression for moment, just keep integrating. The only thing you're going to have to really look to your problem geometry for are a way to solve for those constants of integration. You're always going to have at least two going from a defined expression for moment. And that's where you're going to go back and look at your supports, and you're going to look usually for points where you know that displacement is zero. Like, it's still pinned to the support here. It may be curvy as heck here, but it's the centroid of the beam has not moved up or down. It's tilted. It's that face is rotated, as the whole beam is curved, but it actually hasn't risen up the way it has over here. So you can say, okay, whatever x position this is, my little v is 0 there, and my little v is 0 there. So those are 2 points that you could use to evaluate both of those constants, actually. So to recap, say you knew you were going for beam deflection, and this is a warning. This can get very math-y. So if you wanted to use solvers, or you wanted to write a little computer program to make life easier for you, this might be a great place to do it. But if you started with a distributed load function, you would integrate once to get your shear force as a function of x. You'd throw out one constant of integration. You'd integrate again to get your moment as a function of moment anywhere as a function of x. You're going to throw out another constant. You're going to divide by your tensile modulus and your moment of inertia. Now you have an expression for the first x derivative of your curvature angle. You're going to take all of this divided by EI, and you're going to integrate again. So you're going to kick out another constant. And then, of course, theta is equal to the first derivative of your deflection distance, how high the floorboard is that you don't want to trip over. So you're going to integrate again, and you're going to get a fourth constant. So going from any expression for distributed load all the way through to how much sag do you have, or how high is your beam sticking up, 4 constants of integration. So you have to know 4 things about the beam as you go through, and you're going to use other constraints, your support reactions, or mainly it's going to be characteristics of your support reactions. Can you have shear? Do you have way to support the moment? You know the moment's 0 at one end or the other, and then you're going to know something about the angle, or more likely you're going to know that you have a 0 deflection. It's pinned, it's stuck somewhere usually at 2 points. In fact, it'll have to be stuck somewhere at 2 points if it's simply supported. And if you were able to keep it in static equilibrium, you're going to have 2 points where that deflection is probably going to be 0. So that's going to give you C3 and C4. Okay, so really we had 2 relationships that we kind of harvested from our previous discussion of the Flexure formula, deriving the Flexure formula, and we banked on the mathematical definition of radius of curvature, and just voila, that plus a small angle formula, and we had a second order differential equation that related our moment at any point in the beam to the deflection. So all we're doing is integrating. Let's see, we can do some examples, just get a little bit more familiar with this. The most typical cases are when our product EI, and this is IZZ, is constant along a beam. That's going to be true more often than not. So then, basically the whole analysis or the whole mathematics works is just centering on really integrating whatever expression you have here for M with respect to X. So I will advise you to read through my notes a little bit. I'll just kind of start walking through them. We've really already hit the main points. Again, it's kind of various flavors of integrate 4 times. But if we're starting, we already have an expression for M, starting here. This is kind of looking backwards towards V. If we took the first derivative of M, we could relate basically the third derivative of displacement to our shear force, the fourth derivative of our displacement to our applied distributed load, which basically you could figure out from the previous page. So, we can integral derivative relationships between distributed load, shear force, moment, beam, angle, and displacement. So basically these observations are basically just those statements in words. An important thing, can we or can we not have discontinuities? What would be the actual physical implication of discontinuity? That becomes really important. We can't have them. We have to have a smooth, continuous, differentiable curve. I mean, it's got to be differentiable if we're taking derivatives and integrals, right? What would be the physical implications of a discontinuity? Well, if we had a discontinuity in theta, that means the slope would have to take like a big jump. We would have an abrupt slope change at a point. So this right here that I'm drawing is a discontinuity in theta at this point. And what that manifests is a kink in the beam. The beam would actually kink up instead of just flexing. That would violate our small angle criteria and would violate elasticity. Elasticity doesn't allow for that. That would be the result of plastic deformation and kind of a buckling phenomena, and that would be outside of the assumptions inherent in all of our analysis, including the flexure formula. Even worse is if we had a discontinuity in our displacement. That means the beam broke. That's like a fracture where part of it just displaced upward. So for that reason, we have to assume that our moment expression for x has to be continuous over the span that we're evaluating. If it's not, then we go back and do a piecewise integral, but we would have to wonder about our assumptions, because in that case we would no longer have an intact whole beam. We wouldn't really have a beam. So really make the assumption that it has to be continuous. If you end up somehow deriving a formula for a moment as a function of x that is not continuous over the interval that you're integrating, go back and reconsider your loading. You very likely might have made a mistake. Okay. So we've got an example here. This is super long. So I'm going to hit the highlights and then I'm going to let you step through the numbers. But it is our friendly beam that we analyzed back in our first or second beam lecture, where we were just reviewing our statics. It has an interesting cross-section that we used when we applied our flexure formula example. And so now we're going to go back. We're going to harvest our moment of inertia that we already used. We're going to grab our E. So here's our EI. And here's our moment expressions. We're going to integrate each one of these twice as we go along the beam and look for ways to evaluate our constants of integration and figure out how much the beam is flexing over each of these intervals of position, and then see where the maximum flex is, the maximum displacement. Where's the biggest sag point, or where is it sticking up the most? We can start out by looking ahead and saying we're going to get zero displacement here and here. So our little v is going to be 0 at those 2 points. So we're definitely going to use those. So in our first interval here, under this slope distributed load, our linearly increasing distributed load, to get the angle of deflection at any point, we're going to integrate once, and so we're going to go from a cubed function to a fourth degree polynomial, and we're going to kick out one constant of integration, which is our angle at 0, which is not going to be 0. The beam's probably in fact going to be tilted at a fairly significant angle there. It'll probably be the highest at that end. We'll integrate again. And so we're going to kick out another constant of integration, which is the actual deflection at 0, which we can evaluate. So we're going to carry another one along. This constant ends up being multiplied by x in this expression. Okay, so we basically have two equations. So we could figure out where deflection was a maximum. If we saw where this crossed 0, we could find the zeros of that and see if there's an extrema in our V. And we can move on to our next section of the beam from 3 to 4 meters. So in here between the point load and the end of the distributed load, our moment equation was a line equation. So we can integrate that, and we get a quadratic, and we'll have another constant of integration, basically whatever the angle is at 3 meters, which we could theoretically get if we had that constant. We could just plug in 3 meters there because it has to be continuous, and integrate again. So we'll end up with third order polynomial and another constant. We're adding up the constants. And from 4 to 5, it's again, we've got linear moment expression. We had a little bit different constants because we went past that distributed load. We did not at this point consider our axial stretch load. That would have shifted our neutral axis a little bit, not really significantly, but our displacement and our flexion angle is really only dependent on the moment expression, so not really we can separate our n and our m in this case. So we do the same thing, and we kick out another constant of integration for our slope angle, our flexure angle at 4 meters, and then of course we're going to have our actual displacement at 4 meters. And we know what it is at 5, it's going to be 0. So we've got a flexion, a theta as a function of x, and a v displacement as a function of x over each one of those 3 solvable intervals where we have a different expression for m. So we got 6 equations, effectively 6 unknowns in the form of 2 each constants of integration for each of the intervals. 6 and 6. So we got theta at 0, 3, and 4, and we have the actual displacement at 0, 3, and 4. So we can basically just collect terms. The rest of these steps that I've gone through just show a suggested way of kind of just getting your arms around all of the equations and writing them in a little bit simpler form, and evaluating them so that you can basically harvest everything you can one from the other, to evaluate some of these terms that we can solve from one to the other. Same thing with our expressions for actual displacement. Now we drop in the actual geometry of the problem where we're going to start solving for the unknowns. We say we got pin connections or roller connections at both ends of the beam, x equals 0 and x equals 5. That means our actual displacement is 0 for those. So we had 5 unknowns. Now we got rid of that one. And so that leaves 1, 2, 3, 4, 5. When you include all the thetas, and some of those will be dependent on one another. So I've labeled all the equations, excuse the scrolling. So we have theta at 3 meters, theta at 4 meters, we have displacement little v at 3 meters, and displacement little v at 4 meters and at 5 meters. So that's 5 equations. We have 5 unknowns. So we could solve all of those simultaneously for another. So hence the crank up your solver if you want. These are not, unfortunately, we can't use matrix methods easily on these. These are not linear equations, not even close. In fact, it almost can't be, because the simplest kind of distributed load you could start with is 0. That means you'd have a constant for your shear force. You'd have a linear expression for moment, and then you're going to get a quadratic for theta, and then a cubic, a third order polynomial for your displacement. So the lowest order you could get would be a third order. You'd have an x cubed by the time you got to your little v displacement. So a little bit more complicated. Granted, this was 3 different sections of a beam, so this was a fairly complicated loading scenario. And again, a solver would be capable of taking care of this for you. So that just becomes a mathematical exercise. But the beam physics that we're studying basically tells you what to put into your solver. So focus on that. We will be doing mostly problems in this course that you can do with a hand calculator, simply supported single spans. But in any case, in the case of this more complicated example problem, the solution to those equations ended up, I just wrote them out here, showing, and this is with EI multiplying, you would take this constant and divide it by EI to get theta in radians, or V in this case meters in each case. So we can look here and fairly easily pick off what are the high points. Obviously, anywhere you have theta at 0, you're going to have a maximum or minimum for your actual displacement. For example, in the case of our span under the distributed load from 0 to 3, we crossed a 0 point in theta where the theta angle was 0, flattened out at 2.5 meters. So we'd be saying, aha, that's probably going to be a sag point, a low point, or a bulge. Given that it's a downward distributed load, it's probably going to be the bottom of a sag point, so it's probably a sag. And over the next span, there's no 0 point, so we're not going to expect a low point either, and from 4 to 5, no low point. So we could have a maximum upward or downward deflection at the end points, and then the opposite sign of deflection at our actual mathematical extreme at 2.5. So we can put in 2.5 into the proper equation for deflection over that interval. Don't put it into the one from 4 to 5 or 3 to 4, and then get the actual value of the deflection. And it turned out to be negative 9,336 Newton meter cubed. Then we could divide that by EI and get the max deflection. Now, the nice thing to note is if we had a criteria for max deflection at this point, it can't be more than X. We don't want water in a puddle in a sag, or we can't have it bulging up. Somebody will trip if it's a floorboard. Now we know what we have to adjust the product of our modulus and our moment of inertia to stay below a criteria. So there is some value to keeping our EI product kind of separate from the rest of the analysis. And we can basically do the same thing going through to find obviously where the moment, big M, as a function of x goes through 0, that's where we're going to find our extrema in the slope angle. That may have its own limits as well. So again, just a whole lot of integration and keeping track of limits of integration and knowing where to put them in and take them out. But main focus is your moment. Again, has the big M moment as a function of x somewhere along your beam it's very important both from your longitudinal stress criteria and for calculating max flexural angle and deflection. So moment's really important. Knowing where that's a maximum and being able to express it as a continuous function or as a piecewise function is basically key to being able to determine, is your beam going to work from a longitudinal stress standpoint and from a flexural displacement standpoint, which is really the two most important things you need to know. The third being shear. That's the other direction we haven't looked at. So we've looked at longitudinal things, both deflection and longitudinal stress. The next section, we're going to wrap up that third important part of beams, and that's shear stress. So we're going to look at what's going on. We're actually going to look at our gamma xy or gamma xz is the last component of what we care about. So thinking about what happens maybe up against a support when we've got a distributed load where that V sub x shear force is a maximum, and what's carrying that, and how do we make sure that we don't exceed maximum shear capabilities, as well as effectively our max tensile from the bending flexure. So stay tuned for shear next section.